Alright, today we're going to continue with section 3.4 and looking at some different scenarios with continuity, and then we're also going to start section 3.5 looking at limits to infinity. So moving on to the first example, I want you to practice using the squeeze theorem. So if you're given that c equals a, I want you to find the limit as x goes to c of f of x, given that f of x is greater than or equal to b minus the absolute value of x minus a, and less than or equal to b plus the absolute value of x minus a. Pause the video, try this, unpause it when you're ready to check your work. I will give you a hint, it shouldn't be a ton of work. So pause the video. Okay, so since we're told c equals a, I know that the limit as x goes to c of f of x is the same as the limit as x goes to a of f of x. So if I look at the left side of the inequality, the limit as x goes to a of b minus the absolute value of x minus a is just b by substituting in a for x. So we're just doing direct substitution. I also know the limit as x goes to a of b plus the absolute value of x minus a is also b. Therefore, that's what those three little dots in a triangle mean if you're not sure. It's a symbol for therefore. The squeeze term says that the limit as x goes to a of f of x is going to equal b, since I know f of x is between these other two functions. Or I could say the limit as x goes to c of f of x equals b. And I know that because at the beginning here we said that those two limits are equal. Alright, next let's look at the continuity of a composite function. So if g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x is continuous at c as well. So I want you to discuss the continuity of h of x being f of g of x when f of x is the square root of x and g of x is x squared. And then we'll do part b in a second. So right now just do part a. So pause the video, unpause when you're ready to check your work. Okay, so first I find h of x, which is the square root of x squared, which remember by definition is the absolute value of x. And so if we look back up here, g is continuous at c. In this case, g is continuous everywhere. F is continuous at everything of at g of c, sorry. And that's saying the absolute value of x. So therefore, h of x is continuous everywhere as well. So it's continuous at all real numbers. Part B, so I want you to discuss the continuity of h of x given f of x is 1 over x and g of x is 1 over x minus 1. Pause the video, unpause when you're ready to check your work. Alright, so here h of x is f of 1 over x minus 1, which is 1 over x minus 1, which is just x minus 1. But x cannot equal 1. So h of x in this case is continuous for all real numbers except x does not equal 1, or all real numbers when x does not equal 1. So we know that this is going to be a removable discontinuity at x minus or at x equals 1 because of our resulting composite function. So since our resulting function is x minus 1, which is a line, there are no vertical asymptotes anywhere, it's going to be a removable discontinuity. So again, going back up here to the definition, g is continuous, or g of x is continuous everywhere except for at 1. And so although h of x as a function in itself, which is just x minus 1, would normally be continuous everywhere, it's restricted by the continuity of g of x, which was discontinuous at x minus 1. Notice though in g of x, it was a non-removable discontinuity, whereas in h of x, it becomes a removable discontinuity. Next, intermediate value theorem. We're just going to state it again because this comes up again here. So the intermediate value theorem, if f is continuous, so this is why we're talking about it, on the closed interval a to b, and k is any number between f of a and f of b, then there is at least one number c in a to b such that f of c equals k. Remember, we've done this before. It's good for approximating zeros. A simple, it's good for other things also. But so far what we've used it for, if f of a is negative and f of b is positive, then in between a and b, at some f of c, there has to be a 0, which in this case would be k. But the key thing, or why we're talking about it again, is the fact of continuity. Alright, moving on to other examples. So, let's do a little trig practice. I want you to figure out or evaluate the limit as x goes to 0 of sine of 5x over x. Pause the video, unpause when you're ready to check your work. Okay, so what we want to try to do here, remember, if you were not able to figure it out, is you want to try to get this part right here to fit our pattern of sine of theta over theta. So in this case, since this is the sine of 5x, I need the denominator to be 5x. How do I get that to be 5x without changing the expression? Multiply the top, or the numerator and denominator, by 5. So that's what I did here. So then this 5 in front, I can pull that out in front of the limit. So I can say 5 times the limit as x goes to 0 of sine of 5x over 5x. Well, I know that this piece right here is 1. So this becomes 5 times 1, which is 5. Next one. Find the limit as x goes to 0 of tangent of x over x. Pause the video. Unpause when you're ready to check your work. Okay, so if we initially try direct substitution, we get the indeterminate form 0 over 0 because the tangent of 0 is 0. Now what do we do? Panic? Maybe. But in this case, first I'm going to try to do some trig work. So I know the tangent of x is also the sine of x over the cosine of x over 1. So this becomes the limit as x goes to 0 of the sine of x over cosine of x times 1 over x. If I just rearrange this a little bit or group it, I get the limit as x goes to 0 of 1 over the cosine of x times sine of x over x. Remember that when we have the product of two separate functions that we're taking the limit of, we can do the limit of those individually. So the limit as x goes to 0 of 1 over the cosine of x, and the limit as x goes to 0 of sine of x over x. The limit as x goes to 0 of sine of x over x is 1. We've learned that from the squeeze theorem and because I told you. And the limit as x goes to 0 of 1 over the cosine of x, well, I can plug in 0 for x. The cosine of 0 is 1, so this becomes 1 over 1, which is 1. I end up with 1 times 1, which is 1. Next one. Evaluate the limit as x goes to 0 of sine of 3x over 2x. Pause the video, unpause when you're ready to check your work. Alright, so here we're going to do a technique similar to what I did 2 examples ago, and we are going to multiply the numerator and the denominator by 3 halves in this case because I want this 2x to become a 3x. So I get the limit as x goes to 0 of 3 halves times the sine of 3x over 3x. I can pull the 3 halves out in front. The limit as x goes to 0 of sine of 3x over 3x is 1, and then times 3 halves, which is going to be 3 halves. Next one. Evaluate the limit as x goes to pi halves of sine of x over x. Pause the video, unpause when you're ready to check your work. Okay, hopefully you didn't fall for my trick, and that is that here we can just do direct substitution. We do not get the indeterminate form. So the sine of pi halves is 1, x is pi halves. 1 over pi halves is 2 over pi. Alright, next we're going to look at what's going to become limits to infinity. So if we want to evaluate the limit as x goes to negative 2 from the right of x plus 2 quantity squared, the limit as x goes to negative 2 from the right of x plus 2, and then from the left for both of those, and then at negative 2 and negative 2 for both of those. So to do this, hopefully we recognize right away if we do direct substitution in any of these scenarios, we're going to get 1 over 0. So I can't do direct substitution, but this is only a one-sided limit. So I'm going to look at my calculator now, and we're going to learn a new way to answer this type of problem. So in my calculator for y1, I'm going to put in 1 over the quantity x plus 2 squared. And for y2, I'm going to put in 1 over the quantity of x plus 2. And now we're going to look at the table. So let's change this to... Alright, so we need to change these values. And let's change this to, let's see, we're looking at negative 2, so negative 2.01, negative 2.001, negative 2.0001, negative 2, negative 1.99, negative 1. Oh, I'm sorry, that one should have been let's say negative 1.9999, negative 1.999, and negative 1.9. Alright, so let's look at y1 first. So notice that as the values are getting closer to 2, or to negative 2 from the left, the numbers are getting very, very, very large. So we can think about what's happening there. If we actually look at the graph, we can see that it's going up very quickly. So this right here is the first graph. So normally, what we've done so far is we said the limit does not exist there, because it is technically not approaching a value. But now we're going to use what we call descriptive limits, and we're going to say that it's going to infinity. So this is what we call a descriptive limit. So if I look back here at negative 2 from the right, those numbers are also getting very large. So that's also going to be infinity. Therefore, if it's approaching the same thing from the left and from the right, our limit is going to be the same. So it's going to be infinity. Again, this is a descriptive limit. I do realize I misspoke that I know this one right here, that was from the right, and that's from the left. It doesn't change my answer though, they're both going to infinity. Let's look at what happens on the y2. So on y2, as I'm approaching negative 2 from the right, the values are going to infinity. So this here is going to be infinity. As I approach negative 2 from the left, the values are going down, and they're going down very quickly, so that's going to be negative infinity. Therefore, since these are not approaching the same from both sides, the limit as x goes to negative 2 does not exist. So again, here if I look at the graph for that, I can see that this is from the left and this is from the right. So those are going in opposite directions, therefore they are not approaching the same thing. Again, these are what we call descriptive limits now. But this is, from now on, this is how we will answer these type of limit problems, is if it is going to infinity or negative infinity, you can say that if it's a one-sided limit. If it's a two-sided limit, it has to be approaching that from both sides. What's happening at negative 2? Well, hopefully we recognize that's going to be a vertical asymptote. So let's talk about vertical asymptotes. So again, this is not new. Vertical asymptote, if f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. So let f and g be continuous on an open interval containing c. If f of c does not equal 0, g of c does equal 0, and there exists an open interval containing c such that g of x does not equal 0 for all x does not equal c in the interval, then the graph of the function given by h of x equals f of x over g of x has a vertical asymptote at x equals c. Alright, last example, I want you to find the vertical asymptotes of the following function. So find the vertical asymptotes, don't do anything else, pause the video, unpause when you're ready to check your work. Alright, so here we need to factor to find the vertical asymptotes. So I can factor the numerator into 4 times the quantity x squared plus x minus 6. The denominator I can take out a greatest common factor of x. I factored this over here to the left, so you can see that if you aren't sure how I came up with these factors, but I factored by grouping. So I end up with 4 times x plus 3 times x minus 2 over x times x plus 3 times x minus 3 times x minus 2. Since the x plus 3's and the x minus 2's cancel, those are wholes, not asymptotes. But I'm left with x and x minus 3 in the denominator, therefore I have vertical asymptotes at x equals 0 and x equals 3. So, in conclusion, the squeeze term is important to understand, but don't dwell on it. Intermediate value theorem is going to be coming back now. Trig is awesome, and vertical asymptotes can lead to infinity, or limits to infinity, which is what we call a descriptive limit. End of video.